In focus 4, we start, which is on phase transitions of single substances. You begin to flex your muscles. You begin to say, well, look, I've got all this mechanism and foundation in my pockets. What I now need to do is to see how it actually accounts for the properties of real substances. And the first topic begins with an introduction to phase transitions. Things like vaporization, freezing, and solid-solid transitions, to begin to see how the Gibbs energy, and it's specifically the Gibbs energy really, because on the whole you're interested in systems undergoing transitions at constant pressure, accounts for what you know goes on anyway. And so it begins by looking at ways in which how the Gibbs energy changes when something vaporizes, and looking for the temperature at which vaporization becomes spontaneous at a certain pressure, fixed pressure. You see how the Gibbs energy comes into that. And looking at all the other phase transitions that you encounter in a single substance, which can be, of course, numerous. I mean, there are about 10 different phases of ice, so it's not just this going to that. There's a whole complex of possible phase transitions that one can start to understand, even though you're dealing with a single pure substance. And the way that you portray as it were, the phase personality of a single substance is through a phase diagram. And a phase diagram is simply a map of the regions where each phase is the most stable under the prevailing conditions. And by most stable, we know what that means now. We mean that it's got its lowest Gibbs energy under these conditions. So a phase diagram of a single substance is simply a map showing the regions of where each phase has the lowest Gibbs energy. Then, of course, you've got the boundaries, the phase boundaries, or the so-called coexistence curves, where there is a frontier between one phase and another phase. And in the next topic, what it tries to do is to show that you can predict the locations of those coexistence curves, those phase boundaries, by drawing on what you have done in thermodynamics so far. The first thing that you need to do is to realize that life gets even simpler than it got when you introduced Gibbs energy by focusing on the molar Gibbs energy, which is simply the Gibbs energy divided by the amount of substance in the system. But molar Gibbs energy is a mouthful, and what we do is to introduce the pseudonym for it, which is chemical potential. So for a single substance, the chemical potential is simply the molar Gibbs energy. But chemical potential conveys that sense that there is a potential for chemistry in it. And what I shall gradually do as I go on speaking in this and subsequent focuses is to show that, is to draw out the potential, the chemical potential of the chemical potential. So bear in mind that it's a very good name, and to understand it, all you need to do is to bear in mind what it means. So, for example, the equilibrium between two phases of a single substance is thermodynamically, show from the second law, the condition under which the chemical potential of each phase is equal. So they are, if you like, in opposition, but balanced. And so what you really have to do is simply to find the coexistence curve, the phase boundary in a phase diagram, is simply to map the conditions of maybe temperature or at constant pressure, where the chemical potential of each phase is equal to the other phase. And if you can find that temperature, then you will have mapped the coexistence curve. Chemical potential is all about a tug of war, or if you like, a push of war. That equilibrium is when the potentials are in balance. It applies both to single substances and, in due course, as we shall see, to chemical reactions. Once you've got the equations of how the Gibbs energy depends upon the temperature and the pressure, and of course it's easy to translate that into how the chemical potential depends upon the temperature and the pressure. And all you've got to do now is just to solve the relevant equations to map where the chemical potentials of two phases of the same substance happen to lie together. And this gives you the so-called Clapeyron equation for the solid-liquid phase boundary. And if you're willing to take a further step and introduce treat the vapor as a perfect gas and introduce the approximations that permits, like using the perfect gas law, then you can adapt the Clausius equation, the Clapeyron equation, into the Clausius-Clapeyron equation, and therefore also map the liquid-vapor phase diagram. So you can, and of course you can also do the solid-liquid, liquid-vapor and solid-vapor boundaries, and so you can construct and understand the phase diagram that you've been talking about. So it's really, this particular focus is about taking what you already know about the underlying equations of thermodynamics and also the underlying understanding of what those equations are telling you, and applying it to a single system, a system of a single substance, and looking at the various equilibria that occur within that system and how those equilibria depend upon the temperature. So now understand why things melt as they do, why things vaporize when they do, why some things sublime, and so on. So it really is giving you a hold on these macroscopic properties of the substances.